Welcome to today's session on airplane weight and balance. In this lesson, we'll go through the fundamental concepts, definitions, and practical applications of weight and balance, which are important for both safety and performance in flight operations. As a pilot in command, it is your responsibility to ensure that the aircraft is within the allowed weight limit and CG before each flight. That impacts how many passengers you will be able to carry, how much fuel, how far you will be able to go, how much baggage to allow into the airplane, and sometimes even where your passengers should be seated. Our key references for today will include the Airplane Flying Handbook, the Pilot's Handbook of Aeronautical Knowledge, the FAA's Weight and Balance Handbook, and of course the aircraft's Pilot Operating Handbook. We will use a Cessna 172 as example. Let's get started. Let's start by introducing the concept of weight and balance. What we're talking about here is ensuring that the airplane's total weight and the location of its center of gravity, or CG, are within the safe limits established by the manufacturer. This matters because the airplane's flying characteristics, its stability, controllability, and structural integrity change significantly depending on how much it weighs and where that weight is distributed. Let's imagine there are two people playing in a seesaw, and they want the seesaw to stay level, in equilibrium. Let's say one person weighs 100 pounds and the other 200 pounds. How can we keep the seesaw still when one person weighs more than the other? The answer is simple. We need the heavier person to come closer to the center. But do you know why? Take a look at the picture. In order for the seesaw to remain still, we need all forces and all moments to balance. Starting with forces, the blue arrows pointing down represent the weight of each person. 100 pounds in one side and 200 pounds in another side. The total weight being carried by the seesaw will be 300 pounds, and that is the force that the log in the center of the seesaw needs to withstand. Thus, the arrow pointing upwards. So, we have a total of 300 pounds pushing the seesaw down and 300 pushing it up, by the log, resisting the weight, so there is equilibrium of forces. Next, we need to have equilibrium of moments. Moment is calculated by force times arm, the arm being measured from a predefined reference point. On this example, the reference point will be the log, which is in the center of the seesaw. The person weighing 100 pounds is seated 6 feet from the reference, so there is a moment of 600 feet-pound trying to rotate that side counterclockwise. On the other side, the heavier person is now seated only 3 feet away from the log, so the arm is 3 feet. That makes the moment on that side also 600 feet-pound. However, that moment tries to rotate that side clockwise. As you can see, both moments cancel each other and there is equilibrium. Because there is equilibrium of forces and equilibrium of moments, the seesaw is balanced and still. An airplane is exactly like a seesaw when it comes down to balancing forces. Okay, before we go any further, let's make sure you understand some important definitions. You will hear a lot about datum. This is an imaginary vertical plane. Think of it as the starting point from which all measurements of arms in an aircraft are taken. In the Cessna 172, that's usually the firewall, but it can be defined anywhere, as long as all arms are measured from the same place. Arm is the horizontal distance from that datum to the item or station in question. Station is a location in the aircraft, identified by its distance from the datum. For example, the pilot's seat is a station, the baggage compartment is a station, etc. Moment is simply the weight of an item multiplied by its arm, giving us a measure of its rotational force. The center of gravity, or CG, is the point where the airplane would balance if suspended. Basic empty weight includes the airplane, its permanent equipment, full fluids, and unusable fuel. Max ramp weight is the total weight permitted while taxiing. Max takeoff weight, m-tau, is the heaviest the airplane can be before it lifts off. Max landing weight is how heavy an airplane is allowed to be before landing. This is not much of a factor in a Cessna 172, but it is an important number for transport aircraft, as landing above that weight may damage the aircraft and landing gear structure. Finally, maximum zero fuel weight is the maximum weight without usable fuel. Important mainly for larger aircraft to protect wing structures. Okay, I mentioned before that an airplane is like a seesaw. Take a look at the picture below. As you know, the lift is generated in the wings, and we can represent that as an upward arrow coming out of the center of pressure. The weight of the airplane is represented by a downward arrow concentrated in the center of gravity. As you can see, the CG and center of pressure are not coincidental. This means a moment will be created there, which will need to be counterbalanced by the tail. The horizontal stabilizer and elevator create a small downward force to counter that moment and keep everything in equilibrium. As you can see, this is exactly like balancing a seesaw. And that picture is showing a stable balancing. If the elevator stalls, for example, the nose of the airplane will naturally go down. The airplane will gain airspeed, airflow over the wings, and elevator will increase. And then the forces in the elevator will increase, pushing the nose up or level again. Now, what happens if the weights inside of the airplane are placed way aft and the CG becomes aft of the center of pressure? That's what we call unstable balancing, and you can see it represented in the purple picture on the right-hand side. In this kind of balance, if the elevator stalls or loses some authority, the airplane would start falling nose up. The airflow over the wings would not increase in the direction it should be, so it would be harder, or maybe impossible, to recover from a situation like that. Because of that, manufacturers publish a CG envelope, which shows the minimum and the maximum travel the CG of the aircraft must have, together with the weight limitations. It is your responsibility, as the pilot in command, to calculate weight and balance and ensure the airplane's center of gravity and total weight stay within the safe envelope. If you don't, you risk flying a poorly balanced aircraft, and the consequences can range from poor performance to catastrophic loss of control. Remember, balance is a compromise, and airplanes are designed to be slightly nose-heavy for safety and controllability. Now, let's discuss how weight affects performance. A heavier aircraft has more inertia, making it more stable. This is positive, but comes at a cost. You'll need a higher takeoff speed and a longer runway to lift off. That's because it will take more time to accelerate the airplane until enough lift is created for the takeoff. Your rate of climb will be lower. For the same power settings, cruise speeds will be slower as the airplane will need to fly at a higher angle of attack to generate enough lift to counter the higher weight, creating more drag in the process. This means taking longer to get to the destination, so higher fuel consumption is expected. Your landing distance will be longer as higher inertia means needing a higher ground roll to stop the airplane. Your stall speed will be higher because the airplane is already flying at a higher angle of attack. This means that it can reach the critical angle of attack sooner, before getting to the published stall speed. Also, heavy aircraft can overstress components like the nose wheel on landing and taxiing. Overall, a heavier airplane performs worse, and the same airplane with a lighter load. If overloaded, an airplane might not even be able to climb or reach a safe altitude, and repeated overloading leads to long-term structural wear that can ultimately cause failures. Where the CG is located significantly impacts how the aircraft flies. Let's compare forward and aft CG positions. Starting with a forward CG, the aircraft requires more nose-up elevator force to maintain level flight. That increased elevator deflection requires the tail to push down harder, which translates to more load on the wings. So a higher angle of attack is needed to produce enough lift to counter not just the weight, but the increased elevator load. This results in more induced drag, reducing cruise efficiency. This also increases stall speed. Think about it. The airplane is already flying at a higher angle of attack, so the airplane has less room before it reaches the critical angle of attack. On the upside, stall and spin recovery is easier because the moment arm to the tail is longer, meaning the tail has more leverage to correct pitch, and the forward CG will tend to bring the nose down quicker. Overall, forward CG equals more stable but less maneuverable. Now, with an aft CG, the tail needs less downward force, reducing overall wing loading. This results in lower drag, higher cruise speed, and a lower stall speed. Overall, more efficient at cruise. But here's the danger. Pitch stability decreases. Recovery from a stall or spin becomes harder due to the shorter arm between CG and the tail, and between the CG and the center of pressure. Overall, an aft CG can make the airplane less stable and more sensitive to pitch inputs. How do we control weight and balance in an airplane? First, manufacturers define weight and balance limits as part of the airplane's airworthiness certification process, and these are legally binding. Under FAA regulations, the pilot in command must comply with these operating limitations on every flight. That means we, as pilots, must determine the weight and balance before every single flight. This is the third time I'm saying this, so I can't reinforce this enough. But what if the weight or CG falls outside the limits? Your options are to either reduce fuel, which might mean adding more fuel stops, move and/or remove passengers or cargo. Operators also have the responsibility to update the weight and balance documents after any aircraft modifications, whether it's a new paint job, new equipment, or anything that affects weight or balance. The picture on the right is an example of a weight and balance document provided by the manufacturer in a new aircraft, stating the basic empty weight of the airplane, its CG and moment. Let's now calculate the weight and balance using a real example. The first step is to find the basic weight of the airplane, and that will be in the latest weight and balance document of the aircraft, which is provided by the operator and usually found with the POH. There you will also find the arm and moment of the empty weight. If you only find the arm, you will need to multiply the empty weight by the arm to get the moment. It is important to have a spreadsheet or table where you can write down the location or arm of each station. If you look at the top right corner of this slide, that snapshot in there came from the Cessna 172's POH, and I've already used it to populate this table at the center of the slide. Now let's say the pilot weighs 160 pounds, the passenger weighs 200 pounds, and let's say we will be flying with full tanks, total 53 gallons, which is equivalent to 318 pounds. Remember, each gallon of fuel weighs 6 pounds. In this example, let's say we are bringing 50 pounds of luggage. Adding all up, we have a total weight of 2,448.9 pounds, and that's our total ramp weight. If we assume we will have a short taxi and burn about 1 gallon of fuel before taking off, it means we will be taking off with a total of 2,442.9 pounds. Next, we multiply each weight on the first column by its arm on the second column to get the moment. By doing that and adding all these moments, we will get a total moment at takeoff of 105,151.7 pounds. After dividing that moment by the weight, we find that our CG at takeoff will be located 43 inches from the datum. The final step is to plot that in our envelope, and we will see that both the weight and the CG location are well within the limits, so we are good to go. In some airplanes, as the fuel burns, the CG might travel to an area outside of the envelope. That's why it is also important to calculate the landing weight and the landing CG, with the expected fuel remaining, or even zero fuel, to ensure the aircraft will remain within the approved envelope during the entire flight. What if you, the pilot, calculated all the weight and balance beforehand? Everything was fine, but then, when loading your payload, you realize that you need to make adjustments? For example, let's say the shape of the baggage will not fit in the station you calculated previously, and you will need to move it further aft. Do you need to redo all your calculations? Yes, but you don't need to recalculate it all. You can just make the necessary adjustments. Here's how to do it. First, remove the baggage weight and calculate its corresponding moment. That would be the negative 50 pounds located at the 95-inch arm. Next, add the weight back at the new station in the 123-inch arm and calculate the new moment. Now, add up the removed weight and the added weight, which in this example results in 0 since there was no total change in weight, and do the same with moment. In this example, the moment increased by 1,400 pounds. So you add that 1,400 to the previously calculated total moment, and then divide the new total moment by the new total weight. This will give you the new CG, which you will use to plot again in the weight and balance envelope. As you can see, this is not difficult. Apps like ForeFlight can help us a lot on doing all this before each flight. You will just need to create the proper profile in the EFB using your aircraft's data, and then populate the weights before each trip. Technology makes everything a breeze, but you, as a pilot, still need to know what is being calculated in the background, as you are ultimately responsible for the safety of the flight. And that wraps our lesson today. Thanks for watching. And if you like this content, please consider subscribing. This will help us create more lessons like this.